So this week we are going to see, multi-vibrator, oscillators, and function generator content. So in this week's lecture, uh, the concept of integrator, and Smith trigger all will be used. So please keep that in mind. And in case you have forgot, we can, again revisit. Just let me know. So I hope my screen is visible.
Yes, sir.
Okay, great. So let us begin with, one problem, and then we will see what is required to solve that. And later on, we will converge towards the solution as we do all of in our lectures. Okay.
सर ये कुछ इश्यू है लग रहा है।
It
वो
is
क्या
not being present.
क्या
Okay.
आप लिख रहे हैं वो पता नहीं चल रहा, स्क्रीन में नहीं दिख रहा है सर।
Okay. So that's why. Okay, just a second. So now I guess it is visible, right? My screen is visible.
Yes, sir. This time it is visible.
Okay. Thanks a lot. Thanks a lot for letting me. Okay, so what I was about to draw is, one integrator circuit along with one Smith trigger circuit. Okay, so Smith trigger will have positive feedback as we have seen in our previous lectures. And here also this integrator circuit is connected in cascade with a Smith trigger. Okay, so this value of integrator is 500 microfarad, and this resistor is 2 kilo ohm. Okay, so this positive terminal or non-inverting terminal is grounded in the integrator, and it is grounded at inverting terminal in the Smith trigger circuit. Okay, now here again in Smith trigger it has a positive feedback of 5 kilo ohm. Okay, and this is our output. So basically this kind of signal generator will have the feedback which is connected here. Here output will be connected to the input side. Okay, so this is how it is connected, and it will be used to generate certain kind of waveform which is required for us to feed into some source also, right? So this is our circuit. Now we can segregate first. This proportion is which circuit? As I mentioned, it is integrator. Why integrator? That we will see. This is again 3 kilo ohm, and this is a Smith trigger. Isn't it? So we need to find out certain things. So let me write it down what we need to find out. First thing is that nature of waveform of V1. So V1 will be here. So nature of V1, what kind of waveform V1 will have. And the second thing, nature of V2 waveform. Okay. Third thing is that peak to peak value of V1. So peak to peak value of V1, and fourth is that peak to peak value of V2. Okay, so after finding all that, so these waveforms are periodic, right? V1 and V2 waveforms are periodic, so they will have certain time period. So we again we have to find out the time period of V1 and V2. Okay, so these all parameters we want to identify. So I hope you got the idea of circuit, how they are connected. Any doubt in that, and what are the parameters we need to find out. So let us proceed step by step. Okay, so the first thing is that we have identified that one integrator circuit is connected in cascade with Schmitt trigger. So it will produce certain kind of waveform. So you might have gone through the lecture. So first thing is that what will be the output of the integrator, right? So because here supply of the integrator is itself connected to the output of the overall circuit, isn't it? So you could see that this supply and output both are connected. So both nodes are same. Okay. So now the thing is that V2 is symmetrical circuit and it has certain limit, saturation limit, which will be plus 12 volt or minus 12 volt. Okay. So no matter whatever will be the input at the terminals of a symmetrical circuit, it will produce either plus 12 volt or minus 12 volt. Okay, so it is certain that V2 waveform is what? A square wave. Okay, either plus or minus. So a square waveform. So we are drawing for V2. But for how much time duration it is conducting, that we don't know. So for that, we have to identify this time period. So that is the final part of this problem, that how much for time duration it is going to conduct. So this is the entire time period of V2. Okay, so Niranjan, I hope you are getting. Are you able to understand?
Sir.
Okay, okay.
Yes, sir.
So now V2 is there. Okay, we have identified the waveform of V2. So the second part is actually solved. What is the nature of V2? So what is the nature? It will be a square waveform, isn't it? Now the interesting thing is that how V1 will act now, right? So V1 will be acting as integrator. So what is the integration of a square waveform? You might have studied the signal and system. So what is the integration of a square waveform? If we integrate any constant value or DC value, if you integrate, what will it become?
Triangular waveform.
Triangular waveform, exactly. Excellent. So that will be triangular. Okay, so this magnitude is also saturation limit, that is plus 12 or minus 12. Okay, so now V1 is like this, and why it is happening? So just to be clear, how the integrator circuit works is like, so you can apply KCL at this node. Okay, so from the virtual ground concept, if 0 volt is there, 0 volt will be there, isn't it? So now V2 or V2 minus 0 divided by 2 kilo ohm, or R you can say, is equal to IC. That will be how much? This IC will be how much? IC will be C dVc by dt, right? C dVc by dt. Okay. Now dVc by dt will be equal to 1 by C and R. 2 kilo ohm is R, isn't it? And this is V2. So this is our dVc by dt. Now, if we integrate it on the both hand side, so Vc will be, till V1. So Vc 0 to Vc and T naught to, let's suppose T1 it is going. Okay. So if you integrate, so Vct will be equal to Vc at T0 plus V2 by Rc into T. Okay, and that T could vary till T1 minus T0. So basically, it is having a slope of, if you see this uh, capacitor voltage, VCT is having a slope of V2 by RC. So this is the slope, and this is how it will vary from T naught, right? So from T naught here, in this case, our T naught is 0. So let's suppose that this is the VC0, VC at T0. So it will keep increasing till this point, and once this V2 minus RC, or here, V2 minus RC, V2 by RC, so here V2 once becomes negative, so the slope starts falling down. So this is how it works. Okay. So this will be the nature of V1. Okay. So whatever was asked in part 1, so nature of V1 waveform is triangular. Okay. So these two parts were easy, isn't it? Any doubt, anyone? Okay. So great. It's no doubt. Then we can move on. So the important part is to calculate the time period of both the signals, right? And from this waveforms, you can observe that time period of V2 and V1 both are same. Okay. Why I am calling V1 is equal to Vc? V1 is equal to Vc because this terminal is 0 and this is V1. So 0 minus V1 is equal to minus Vc. So that in that way it is equal. So how to calculate time period? Any idea?
टाइम कांस्टेंट निकालेंगे.
ओके या संगीता, सो टाइम कांस्टेंट निकालेंगे किसका, V2 का या V1 का या दिस RC सर्किट का?
RC सर्किट का.
RC सर्किट का. Great. So we will find out the time period. Yeah, right. Let's see how to proceed. So we have the value of slope, and what is this value of slope, that also we need to find out. So this slope will vary from any limit. So this consider as LTP, and this consider as UTP. Okay, because we don't know the peak value or the peak to peak value of V1, do we? We have to also find out the peak to peak value of V1, right? So how much will be, the first thing is that how much value will be of peak to peak value of V1. Okay, first thing, if we know, then we know the slope, right? Once we get to know the peak to peak value of this V1, then we also get to know the value of slope, right? And then we can easily find out the slope. Okay. So for that, we can do, if you see this circuit very carefully, okay, I think we can solve it. Isn't it? Or do you have any other idea? Like Sangeeta said that time constant nikalenge, but in that case, time constant will be required where you have certain finite time. So basically, this in this circuit only capacitor is there. Here you can see on the feedback side only capacitor is there. So that is why it is ramp slope. Otherwise, it should have some exponential increment. So that approach, I don't think should work here, because here, if you see the time constant, tau is equal to RC. So R is 0 in this circuit, right? Here, no R is connected. So in that way, our time constant will be how much? 0. Means it is
Zero.
yes, yes. So we have to look for any other approach. So any other approach from this circuit you can look at from the Schmidt trigger. So we know for
UTP
certain.
minus
Yeah, go ahead, please. Yeah.
UTP minus LTP by slope, एक ये भी एक तो फॉर्मूला था, देखे थे लेक्चर में.
या सो फॉर्मूला याद करने पे ऐसे होता है, हम लोग भूल जाते हैं, बट इफ वी सी द सर्किट यू कैन
Yes,
सी,
sir.
राइट. सो यहाँ पे क्या होगा, यहाँ पे जो स्लोप है, पहले तो VP कितना है वी हैव टू फाइंड आउट, राइट. और VP can we find out if we know this value of V1? Remember from a Schmidt trigger lectures where we were solving some problems based on the Schmidt trigger. So first, so we will apply voltage division rule here. Vp is equal to V1 into 5 kilo ohm plus V2 into 3 kilo ohm divided by 3 plus 5 kilo ohm.
Yes, sir. Right, sir.
So
Yes.
that voltage division rule we will apply here. I hope everybody is getting, right, Sangeeta? NS?
Yes.
Okay, great. So Vp is equal to, I am going to apply voltage division rule, V1 into 5 kilo ohm plus V2 into 3 kilo ohm divided by 8 kilo ohm, 5 plus 3. So that I am going to write here. Vp is equal to V2 into V2 into 3 kilo ohm plus V1 into 5 kilo ohm. Divided by 8 kilo. So this is one thing, okay? Now we know that Vp is going to be equal to 0. How? From the virtual ground. Here see, it is 0, 0. Okay, so we can equate to 0, right? So now let me equate it
Sir,
to
0
0.
कैसे होगा सर वहाँ पे?
यहाँ पे
Sir.
see, inverting terminal is connected to ground. So from the virtual ground concept, can we do that? Here you can see.
ये तो नॉन इन्वर्टिंग है ना सर?
Non-inverting है. फिर भी if you apply KCL, okay. So what is the impedance of this circuits? If some in non-inverting op-amp, if some resistance were connected, used to be connected here, right? Then we cannot apply this kind of virtual ground concept. But here we can apply. So you tell me why can't we apply virtual ground concept here? Niranjan?
Yes, sir.
So you were saying that we cannot apply virtual ground concept here, right?
Yes, sir.
So the region, do you know, like any other region? So I told couple of conditions should be there to not apply virtual ground concept. So if both the terminals are connected with different or different kind of source, right? If let us suppose VP is connected to the different source and V1 is connected to different source, in that scenario we can apply virtual ground concept. Okay, but here V inverting terminal is connected to ground and VP is there, right? So here no conflict is happening between both the terminals. It is not going to happen, or it is not going to contradict anything if you write here VP is equal to VN, right? So remember most of the Schmidt trigger circuit, both terminals used to be connected with different supply. If you remember correctly, I asked condition for Schmidt trigger circuit. So you said that positive feedback should be there. But again, I mentioned one more condition you should consider, that both terminals must be connected with different supply. Do you remember?
Yes, sir. Yeah,
Okay.
yes, sir.
Yeah. So that is why, first question, if you remember, some common supply was there, VI kind of. In that scenario, you cannot apply.
Okay,
Okay.
sir.
Okay. So that is what we are going to use here. And we are going to find out the value of V2 in terms of V1. V2, 3V2 is equal to minus 5V1. Okay, so V2 is equal to minus 5 by 3V1. Okay, so it has one expression as well, that V2 is equal to, V supply into R1 by R2. So this is the expression must be, taught by the professor. So this is what we can also derive from the, just by seeing at the circuit. So if you can't remember, if you remember, you may forget, but if you just observe the circuit here, so you just need to, equate both the terminals and the slope of VP, right? And we can apply superposition or, voltage division rule here at VP, and you will get easily this expression. V2 is equal to minus 5 by 3 V1. Okay, or this V1 is equal to so no, this is in other terms. So this is correct. This is from the formula. So here, which one is the supply, V2 or V1?
V2.
V2, exactly, excellent. So V2 is the supply. V2 will be, either plus 12 or minus 12. So that's what happens with, remembering. So V1 is equal to minus 3 by 5 V2. So now we can say R1 by R2 into V supply. So that was the expression. Okay, R1 was 3, R2 is 5 kilo ohm. See, this is the R1, this is the R2. Okay, so now we are good to go, right? We have calculated the relationship between V1 and V2. Okay, and we know one of them. If we know this V2, because V2 is either plus 12 or minus 12. So V2 will be, V1 will be equal to, let us consider minus 12. In that case, they will be plus, so 36 by 5. So that will be 7.2 volt. Okay, so that is the value of V1. Okay, if we are considering which one, if we are considering minus 12 volt. At minus 12, V1 peak value of V1 will be 7.2 volt. So at minus 12, let me modify this waveform. So this is 7.2. Okay, when V2 is minus 12 volt. Okay, let's see if V2 is plus 12 volt, then it will be equal to minus 7.2 volt. Isn't it? Is there any doubt in this?
No, sir.
Okay, great. So one thing is certain that, okay, let us first see. No, this is wrong because time period of this signal will be double of the source. So when at minus 12, it is plus 7.2. At plus 12, it is minus 7.2. So the transition is happening here. So it should come at this point. From this to this, isn't it? This is how transition should happen. And it should repeat. So here it is changing from, plus 12 to minus 12. So as soon as it will change, our integrator has, 0 time constant. So it will immediately reach at that point and it will reach till 7.2. So minus 7.2 to plus 2. This is how this waveform will look like. Okay, I hope you are not getting confused with it. So this is the time period of V1 as well. So one thing we can observe here that time period of V2 is equal to time period of V1. So if we are able to calculate one time period, we will be able to calculate the other. Okay, and since it has been distributed equally, so because why we are saying that this time period is equal to they are distributed equally, because the supply is varying from plus 12 to minus 12. Okay, so depending on that, they are distributed equally. So how we will calculate time period of it? So time period will be equal to, how much slope it is rising using one time constant like this T1. If we can consider, we can multiply it by 2. Okay, so UTP minus LTP, this is UTP, this is LTP. Okay. Yes. So this is the slope and this is the T1. Okay, this is the T1 and this is slope. So we know this slope, right? So 7.2 minus 7.2. So that I am going to write in terms of UTP minus LTP. Okay, divided by slope of V2, right? So how much is the slope of V2? How much is the slope of V2? Or slope of V1? Here, slope of VC, slope of V1. What is the slope? We know in terms of numbers, but in terms of expressions, in terms of capacitor value, if there is finite capacitance, then how much will it be?
RC.
Yeah, exactly. So V2 by RC. So this slope of V1, isn't it? So it will be UTP minus LTP divided by V2 by RC, or V supply by RC. Okay. why I am writing slope of V1 is equal to V2 by RC. If you are not able to get, you recall this, V1 is equal to nothing but, 1 by RC V2 dt. Okay, from here you can see that the slope is 1 by RC or V2 by RC. Okay, so this is the time period is equal to 2 into this width T1, right? So we will have to multiply 2 into RC into UTP minus LTP divided by V2. Okay, so UTP and LTP we have already calculated, that is 7.2 and minus 7.2. Okay, and if you want to write in terms of supply, so V2 is equal to V supply, so you can consider it as 12 volt plus minus. Okay, now our expression is just we are gonna plug all the values, right? UTP minus LTP, so the time period is equal to UTP minus LTP into 2RC divided by V supply. So we have simplified in terms of this value. Okay, and can we further simplify 2RC V supply UTP? Okay, first let us solve. So 7.2 UTP minus LTP will be 2 times 7.2, which we have calculated here, divided by V supply is 12. So this is nothing but this slope, right? This slope, this value is nothing but this slope. Please be there. If you are not able to get, I can explain once more. So this UTP minus LTP and this V supply. So C, this is nothing but 2 into R into C. So how much is R here? So R is 2 kilo ohm and this one C is 500 microfarad. Two into 2 kilo ohm into 500 microfarad. So if you calculate it, you will get the value of time period. Okay. So how much will it be? And 2 into 4, 8. So it is going to be 2.4, isn't it? So 2.4
2.4.
second. Okay, you are also getting 2.4 second. Okay, so this will be the answer, and I must know there might be some confusion happening at your end because this expression is slightly different than the derived by the professor. Basically, it is one step earlier than the final derived expression. So the relationship between UTP minus LTP divided by V supply. Okay, so that is what is going to happen in terms of UTP minus LTP. Okay, that we can write as 2 times V supply, isn't it? And divided by V2. or V1, slope of V1. Slope of V1. So slope of V1. So slope of V1 we have derived here, right? Slope of V1 is from this expression. Slope of V1 is R1 by R2 divided by V supply. So into V supply. And into 2R. Okay, now if you cancel it and if you will be calculating, so 4 into R into C into R2 divided by R1. So this is the expression. If you directly plug in all those values, you will directly get your result. Okay, so no need to worry. Any way you can take. Okay, there is not at all any issue. Okay, just you have to ensure, you have to remember which one is R1, which one is R2, which one is R. So in that way, the most simplified version you are able to remember, or you are able to, understand in that way, that would be better. Okay. So shall I repeat it once more, this problem?
Yes, sir.
Yeah. So I was also hoping for that because it is quite messed up. So let's simplify it. Okay. So basically, all the terms are fine. Just, we have to get the time period, and to calculate the time period, we have to equate Vp is equal to Vn. First thing is that Vp is equal to Vn. So the first step was Vp is equal to Vn, and from the voltage division rule, we equated it as equal to 0. So Vp is equal to nothing but V1 into 5 kilo ohm plus V2 into 3 kilo ohm divided by 8 kilo. So the first thing we did here, right? We equated to 0. Now we are able to get V1 in terms of V2, and V2 will be either plus V supply or minus V supply, either the plus V saturation or minus V saturation. That is either plus 12 or minus 12 from this problem. So V1 we will be able to get, okay? That is either plus 7.2 volt or minus 7.2 volt. So I hope till this point you are clear. The value of V1.
Yes,
Is
sir.
that okay? That you can also write in terms of expression, that is V1 is equal to R1 by R2 into V supply, because V1 has certain slope, so it will increase and fall according to the slope. So if you are solving directly, you can just proceed from this value. Otherwise, you can go ahead with the expression. Either way is fine for us. So once we are done with V1, now what we can do? So we have to find the time period. So if we calculate the slope from this expression, right? What is the slope of the V1 or VC? So we all know that any capacitance branch or any RC circuit will have the slope of 1 by or V by RC into dt from the integrator, right? So T0 to T1, this is the work of integrator, right? It will integrate, and it is the slope V by RC, okay? So the slope of V1 will be, how much? V supply divided by RC, because it is integrating nothing but this V2, this VC here. This is integrating nothing but this V2. Okay, so that is why I am able to call this slope as V by RC and nothing but V2 by RC. Is it fine till this point?
Yes, sir. Clear, sir.
Okay, so once we got this slope, okay, once we got the value of the slope, we know the peak to peak value. Peak to peak value is how much? UTP minus LTP. So slope is there, slope is there, perpendicular is there, base is there. So from the expression of tan theta, slope is equal to perpendicular is nothing but UTP minus LTP, okay, divided by this 2 times or T1, first of all, T1, okay. Now we know the value of slope V2 by RC is equal to UTP minus LTP divided by T1, okay. I hope you are following. Now time period is nothing but 2 times T1, okay, and 2 times T1 is equal to 2 times UTP minus LTP divided by V2 by RC, okay. So this is expression, either you directly plug the value of UTP minus LTP and V2 you anyway know the supply, or you can calculate it, or you can further simplify. So UTP minus LTP relationship here I have, derived here for you. So the slope of V1 either you can plug in directly, right? So here we have written 2 times UTP minus LTP into RC divided by V2. Okay. Now we know the relationship between UTP and LTP. They are 2 times of UTP or 2 times of LTP, you can say, right? UTP is equal to LTP. Then LTP, then this expression will become two times UTP. Okay. Now the relationship between UT and V2 we have calculated, right? So UTP is nothing but V1 peak. Okay, till this point it is fine.
Yes, sir.
2 times V1 peak. Okay. Now the relationship between V1 and V2 we have calculated in terms of V1 by V2 we have calculated in terms of R1 by R2 into R1 by R2. Okay. So you just need to plug in here is equal to 4 times, UTP minus LTP into V1. V1 is equal to nothing but R1 by R2 into RC. So that is the overall expression of the time period. So frequency will be inverse of that. So R2 divided by 4 R1 into R into C. Okay. So this R is nothing but the integrator circuit register. This register, this is the R. Okay. And R1, R2 is the register connected to the Schmitt trigger circuit. Okay. So that if you are able to recall, it's better you can just solve within one expression or one sentence or 1 minute. Otherwise, you can derive it at any point of time and you can get the value. Okay, so I hope it is fine for you. Any final doubts? Shall I repeat once more? So
No, sir.
here, okay, great. So time period we are able to calculate, that was 2.4 seconds, right? Now, what is the peak to peak value of V1 and V2? This third and fourth part.
सर स्क्वायर वेव का तो 12 माइनस ऑफ माइनस 12 24 वोल्ट आएगा और ये इसका तो पता ही चल गया 2 into 7.2
7.2, yes. So V2 का तो आएगा 2 times 12 which is 24 volt and V1 का आएगा 2 times 7.2 which we have calculated by the way, isn't it? So that will be 14.4 volt. Okay. So we are done with this part, this problem, isn't it? So any final doubt before moving towards the other problem?
No, that's sir.
Okay, great. Thanks. So let us move ahead. One final thing. So this will be the frequency of the circuit, isn't it? This will be the frequency of the circuit. So one part is that we have certain degree of freedom, right? But we can adjust the frequency of these signals without affecting their amplitudes. So if we have to achieve that, let me write it for you. Affecting amplitude of the circuit, we have to change frequency. Which parameter we can change?
Resistance.
Resistance. Which one? We have 3 resistances in this circuit. And we have this expression of frequency. We have finally calculated 4 times RC into R2 R1. So we can change anything. We can change all 4 parameters. But the condition is the amplitudes should not be affected.
सर आर होगा
R होगा exactly. So R होगा, why R होगा?
क्योंकि जो ये है ना जब हम B1 निकाले थे तो R नहीं था R2 R1 था
Yes, exactly. So V1 in terms of V2, if we calculate, the slope is R2 R1 by R2. So there R is not coming. Hence, we can tune the R accordingly. We want the time period or the frequency of the circuit. So excellent, Sangeeta. That is quite good observation, right? So we can vary R this resistance. This will not come if you calculate the relationship between V1 by V2, which will R1 by R2. So here R is absent. Hence, we can change R, so it will not affect the amplitude of this circuit. Okay, so is it okay for you, NS and Niranjan?
Yes, sir. Okay, sir.
Okay, great. So moving ahead. Okay, great. Let us move to the next part of IC 555 timer. So again, I am going to pose a problem here, right? And then we will look behind the concept of that. So what is the problem here? This is how this circuit is made. Third one should be capacitor. Okay, and it is connected to plus 9 volt of supply. Okay. Now 2 op amps would be here. Again, another parallel branch will have 3 resistors. Okay. Now this is also connected with plus 9 volt. Okay. Now 2 op amps will be here. And both the op amps are connected to SR flip-flop. So just by looking at this circuit, it might be looking as very huge circuit, but it is not like that. It is very simple. and both the terminals are connected. So the non-inverting terminal of the first op amp is connected to the inverting terminal of the second op amp. Okay, and whatever the voltage is here, so this is VC. Okay, and now this VC, and just one step above, it will be connected to one transistor, NPN transistor. Okay, and this is connected to directly to the output. So the reason behind connecting this transistor to output, that it can determine when the circuit, when this transistor is on or off. Okay, so to be on, it has to be forward biased, or to be off, it has to be reverse biased, in that fashion. Okay, let me give the values of all the resistors. 2 kilo ohm, 2.5 kilo ohm, and 0.25 millifarad. Okay, and in second branch, all resistance values are 5 kilo ohm, 5 kilo ohm, 5 kilo. Okay, and this are connected to plus 9 volt, minus 9 volt, plus 9 volt. So whatever the supply is there, right? This plus 9, plus 9. So this is how the circuit IC555 A-stable multi-vibrator circuit is given. Okay, we'll see what are A-stable and monostable and bistable. Okay, so what are we required to find out? That let me write. So first thing is that peak to peak value of VC. Okay, so this is the first part. Now we have to find out the second thing. When VC is rising, because VC is the capacitor voltage, either it will rise or fall. Okay, so when it is rising, then the nature of V out. Okay, similarly, when VC is falling, nature of V out. Okay, now the off time or low time. So what is off time? That also we will see. Off time or low time of V out. Okay, last one is on time of or high time of V out. Okay, so this much we have to calculate. Okay, and again finally, what is the frequency of output? So if we calculate on or on and off time, if we will sum them up, then we are going to get the overall frequency of the output. Okay, so this is how this circuit looks like. You know, in first branch, first parallel branch, we have two resistances and one capacitor. In second parallel branch, we have three resistances. Okay, and the connection, yeah, so connection is done here. Connection is the first branch is directly connected to output via one transistor, and second branch is connected to, you know, op amp. So positive terminal of this op amp is connected to here. Okay, so two op amps are connected to the second parallel branch. So how they will work, that is the first thing. So actually output is connected to S or R, S and R, S R flip-flop. So it will be either high or low. Oh, okay, so once S is high, it means, see, when S is equal to 1, V out is high. When R is equal to 1, V out is low. right? From the set and reset. So S means set and R means reset. That's what they mean in SR flip flop. Okay. So now just let me copy this circuit once more so that okay. So when S will be 1 or when our output will be high and when our output will be low. So our output will be high when S is equal to 1, which means this we have two comparators connected. Okay. So we have to see when both comparators will be high and low, first thing. Okay. So we have to proceed with one assumption. Let us assume that output is low. Okay, let us assume output is equal to low or 0, which means R is equal to 1. Okay, so what will happen in that scenario? That output will go here, it is low, which means our transistor will be off. Okay, so if output is low, so this is connected to low, so this will be off, this transistor will be off. In that scenario, what will happen? This capacitor will be connected directly to the supply, and capacitor will integrate or it will rise. Okay, so this current will flow because this transistor is off. So we are looking at the first case, and output is low. When output is low, our transistor will be disconnected. Okay, and there will be one current flowing in that branch, which will be basically integrating. Okay, and till what value it will integrate? So that is basically VCC, or the supply, divided by this current at a steady state. What will be there? So it will be 9 divided by R1 plus R2. Okay, so this capacitor 0.25 millifarad will charge through these both resistances, RA and RB. So 2 and 2.5 kilo. Okay, so this is how they will charge. Once it will go above the limit, okay, so that limit is decided based on how much is the limit. So see, this limit is 2 VC. The negative terminal. So here the concept of comparators will be used. So this negative terminal will be how much? 9 divided by 9 into 10 divided by 15, right? So
6.
yeah.
6 volt.
So 9 into 10 divided by 15. So it will be 6 volt. Okay. And this terminal will be 9 into 5
volt.
divided by 15. So 3 volt. So basically it is nothing but we supply into 2 by 3, and it is nothing but exactly. So we supply by 3. Okay. So this is how they are connected. Yeah, and this capacitor is connected in this way. I forgot to connect this capacitor. This capacitor is connected from here to the non-inverting terminal of the first comparator and inverting terminal of the second comparator. because this capacitor has to either rise or fall, and it will compare both the values. If the VC is falling, it means it is disintegrating, and if VC is rising, it means it is integrating. But when that is happening, that will depend on the output side. I hope you are not getting confused here. Okay, any doubt till this point?
No, sir.
Okay, great. So now we know both the values, right? V supply into 2 by 3 and V supply by 3. So if VC, let me write it, if VC is higher than 2V supply by 3, it means the output will be plus 9 volt. Okay, and this S will be equal to 1, and our output voltage will be high. Are you able to grab this point?
Yes, sir.
Okay. Similarly, if VC is less than 2 by 3 V supply, then output will be,
Minus
then in that case,
9 volt.
output will be minus 9 volt, right? So output of comparator 1. So here let us say V comparator 1. So V comparator 1 will be equal to minus 9 volt. Okay, which means it will reset. Okay, and our output will be low. And when that is happening, so here for the second comparator, this was for first comparator. Any doubt in this?
No, sir.
No, sir.
Okay, good. So let's moving ahead with the second comparator. So second comparator will compare with this V supply by 3, isn't it? So if V supply by 3 is higher than, sorry, if VC is lower than V supply by 3, then what will happen?
Plus 5 volt. Plus
Yeah,
9 volt.
or
Sir.
V comparator 2 will be plus 9 volt. Okay, and if VC is higher than V supply by 3, V comparator 2 will be minus 9 volt. Okay.
Yes, sir.
Okay, so we have the conditions for both the comparators. Now we have to plug in those values in S and R, and we have to see that when they are going to produce output high. So basically, second my AirPod. So this term I have to delete. I'll let you know why. Okay. Now we have to feed S or R. So S or R will either take 1 or 0 from the flip-flop terminology. Okay. So S will be equal to 1 when output of comparator will be plus 9 volt. So S will be equal to 1 when V comparator 1 is equal to plus 9 volt. Only when S will be equal to 1. And in that case, V output will be high. Okay, I hope this is clear. The second terminology is output will be low when R is equal to 1. It means it will reset at that point. So R will be equal to 1. So at R is equal to 1, what is the value of comparator 2? So this is when R is equal to 1, when Vc is less than Vcc by 3 or V supply by 3. This is when R is equal to 1. Any doubt in this point?
No, sir.
Okay. So R is equal to 1 when V comparator 2 will be equal to minus 9 volt. Okay. Now, sorry, plus 9 volt, not minus. We are focusing only on positive. Okay. Not on the negative, because there is no meaning of negative. Even if R is equal to 0, it means it doesn't guarantee that your S is equal to 1. So they are not complement of each other. Hence, we are not focusing on the negative. So we are focusing when the output of comparators are positive. When they are negative, then what will happen? That also we will see. Okay. Then in that scenario, our capacitor will be charging, but that we will see. Okay. So now to satisfy both the conditions, so when are they happening? V out is equal to high and V out is equal to low. So when V comparator 1 is equal to plus 9 volt, then output voltage is high. It means what is the condition? When it is plus 9 volt, when Vc is higher than 2 by 3 of V supply. When Vc is higher than 2 by 3 of V supply. And the second condition, when V comparator 2 is equal to plus 9 volt, V comparator 2 is equal to plus 9 volt, when Vc is less than V supply by 3. When Vc is less than V supply by 3. Okay, these both conditions we have to look out. Only these two conditions. That will determine our output. Any doubt in entire period, anybody? I can explain once more if you just let me know. This may be complicated, messy, but at the end, they are very simple. You have to just look at the comparator. So what is happening when output is becoming low? Okay, just look at the chat box. Second, comparator non-inverting terminal is not connected. Oh yeah, NS. Yeah, I was able to observe at that time, so I connect. Thanks for letting me know. So yeah, when our output is high, it means this transistor will be on, and at that time this capacitor will be short circuited. So this capacitor will discharge with this 2.5 kilo ohm, right? This capacitor will discharge in that way when this transistor is on. And when the transistor is off, this capacitor is getting charged by this both the distances combined, 2 and 2.5 kilo. Is that okay?
Yes, sir.
Okay. So I am expecting that there is no other doubt. Okay, NS. NS, you're also able to get. Sangeeta, Jyoti, I hope you are able to get it.
Yes.
So okay, great. So let us move ahead. Let us, see the output waveform, and based on the output waveforms, we will be looking at the capacitor or VC. Okay, so assuming as output voltage is high, starting from high, and low, high, because this is how this will go on. But frequency we don't know, and also duty cycle we don't know how much the time of on and off. So that we will have to calculate, and that is what our question is all about. On time for high output voltage, off time or low time of output voltage when VC is falling, nature of Vout and all. So we will be able to calculate based on this waveform. So this waveform is very important. If you are able to get this waveform, you will be able to calculate all the parameters. Okay. So we also don't know these magnitudes. So high, low, just I'm writing high, low. Okay. So this is the nature of output voltage. So what about VC? How this VC will vary? So VC will either charge or discharge. Okay, that is for sure. When this output was high, isn't it? When this output is high, this output,
discharge होगा sir.
then yes, then it is discharging. Okay, so then it is discharging. So it will discharge in certain fashion with certain value of slope that will be exponentially, it will discharge because the resistance is connected. Okay, and when output is low, then what will happen to VC? When output is low, then what will happen to VC? And here
Charge
it
होगा
is,
sir.
yeah, it will charge exactly. And here it is discharging with the resistances. Here it is discharging with resistances only this 2.5 kilo ohm. Discharging through 2.5 kilo ohm, and here it is charging with the resistance 2 plus 2.5 kilo ohm, right? Both the resistances. So 4.5 kilo ohm. So do not get confused. Let me write it. Charging with, discharging 2.5 kilo ohm and charging with 4.5 kilo ohm. So if there is high resistance, okay, so which rate will be faster and which rate will be slower? Charging will be slower or discharging will be slower here? So the resistance is high. Charging will be slower. Excellent. Yeah, charging will be slower, or charging will take very, what to say. I'll see. So if R is higher, this time of, time constant is higher. So this rate will be, slower compared to the discharging. So rate of charging will be, high, slower, because it has more number of resistances. Rate of discharge. Okay. So this is how it is going to charge. Now we are interested in this magnitude as well as this time period. So let us consider this T on and T off. If we are able to calculate both time, T off and T on, we will be able to calculate time period. Okay, and we are interested also in this magnitude. This magnitude. Okay. So it will start charging from certain initial condition, and why I am indicating like in that fashion, because we had two conditions. When output is high, in that condition, what is happening? When output is high, then VC is higher than V supply 2 by 3 of V supply. Okay. So when output is high, it is discharging. So peak value of VC will be nothing but 2 by 3 of V supply. Okay. Then only it will discharge. Basically, this output is high. It means the capacitor is connected through the transistor, right? And it is discharging through the transistor. And at that time, output is equal to, or VC is equal to, it should be higher than V supply. Okay. And it will charge when our output is low. Okay. Then it will charge, and it will charge when this value is V supply by 3. So VC is less than V supply by 3. Okay. Then only it will charge. Are you able to get it? Both the points, both the data points. However, if as soon as it exceeds this value, this is 2 by 3 V supply, isn't it? As soon as it exceeds that point, then what will happen? It will again start discharging. But it has tendency to go till V supply. Why? Because in RC circuit, in any RC circuit, it has the tendency to go reach till the supply voltage, right? So here nothing but this capacitor is connected to plus 9 volt. This capacitor is nothing but connected to plus 9 volt. So it has a tendency in infinite time to reach till 9 volt. Okay, but it is being stopped forcefully by the connection of the circuit with the help of comparator and SR flip flops, that it is being restricted till 2 by 3 V supply. Okay, and again it has tendency to fall till 0. Okay, but it is being restricted at 1 by 3rd of V supply. Okay, are you able to get these points? Any doubt?
Yes, sir. Okay.
Oh, okay, great. Just let me see the chat. Okay, charging will be slower. Yeah, exactly. Rate of charging is less than rate of discharge. Yeah, miss. So that is true. Okay, so if you are able to get it, now let's move towards the calculation of measurement of T on and T off. Okay, so how will we calculate? So at the point of T off, so let us consider certain time instant. Okay, so when it is getting charged, so let us consider this is at 0. T is equal to 0. This is T is equal to T off, right? So if we are able to calculate magnitude of voltage at T off, then we will be able to calculate the time. So let us see. So VC at T off at this particular instant, VC at T off is equal to how much? At this particular instant, VC value is how much? 2 by 3 of V supply, isn't it? Now we can incorporate the expression in the expression. So how will be the expression? So from the transient of the network analysis, you can see VC at infinite plus VC of 0 minus VC at infinite e raised to power minus t by tau. And here at the place of t, I can write T off. Isn't it? Is there any doubt in this part, this step? How I am able to write this?
No, sir.
Okay, cool. So let us proceed. Okay. So 2 by 3 V supply. What is the value of VC infinity? It is charging and it will go until we supply, isn't it? What is value of VC0? VC0 at t is equal to 0. This is the initial point, right? So initial value is V supply by 3.
130 V supply.
Exactly. This also, we know V supply is to power T of tau. Tau we know. Since this is charging, so what will be tau? 2 plus 2.5 kilo ohm, which is in terms of expression Ra plus Rb. It is charging through two resistances into C. So here we can equate to V supply plus V supply by 3 minus V supply e raised to power minus T of divided by tau. That is nothing but Ra plus Rb into C. Okay, I hope it is smooth till this point. If there is any doubt, just ping me. Okay. Yeah, one message. Okay, nice. Yeah. So now I am simplifying it. 2 by 3 we supply 1 minus 2 by 3 e raised to power minus T of divided by Ra plus Rb into C. Okay, I hope it is fine. Now, if you further simplify it, V supply will be cancelled out. So 2 by 3 e raised to power minus T of divided by Ra plus Rb into C is equal to 1 minus 2 by 3 will be equal to 1 by 3. Okay. So, so this 3 and 3 will be again cancelled out. So e raised to power minus T of divided by Ra plus Rb into C is equal to 1 by 2. Okay, now we will take log on both sides, right? So ln e raised to power minus T of divided by Ra plus Rb into C equal to ln half, okay, which also you can write as minus ln of 2. Okay, that is the property of logarithm. So minus T of ln into E will be cancelled out, minus T of divided by Ra plus Rb into C equal to minus ln2. Okay, so this minus will be cancelled out. So T of will be equal to Ra plus Rb into C into ln2. Okay, in our case, Ra plus Rb is nothing but 4.5 kilo ohm. Just here we can calculate into value of C is given, right? 0.25 millifarad, if I remember correctly. Yeah, 0.25, so 250 microfarad. So if you calculate it, how much you will get, please let me know. 240.25. $1.125 into 2. So 0.7797 seconds. So this we have calculated off time. Okay, when capacitor is discharging. Okay, when off time means capacitor is capacitor is charging, then only it is off time, right? Off time means output is low, and when capacitor is charging. So we have calculated this T is equal to T off. This T off is 0.77. Any doubt in calculation of T off in entire process?
No, sir.
Okay, great. So I hope everybody is cool with that. So let us calculate the on time. Okay, so that was the low time of output. Okay, so I hope you got the idea of what do we mean by off time of output. So here we can write off time of V out. So off time of V out is 0.7797. This we have to. Now let us proceed with the on time. So now what we will do? Oh. So now here what we can do, that we can shift this T is equal to 0, and we will consider this point as T is equal to 0. And here T is equal to T on. So this is the period of T on. Okay, this is the period of T on. At T on, our capacitor is getting discharged. Capacitor is getting discharged with the only one resistor. Okay, our capacitor is getting discharged with only 2.5 kilo ohm resistor. When output is high, it is connected to transistor which is high, and it is short circuiting here, and our capacitor is discharged in this fashion. Okay, so now we have to calculate the slope. Okay, so now again we will do the entire phenomena, right? So VC at T on, VC at T on. Okay, so VC at T on is how much? VC at T on is how much? V supply by 3. Am I right? Okay, nice. Yeah. So VC is equal to V supply by 3. Now again, we can equate it with our tangent expression. VC infinity plus VC 0 minus VC infinite e raised to power T on divided by tau. So VC at infinite, how much will it be this time? During charging, we considered till at infinite instant, VC will be equal to V supply. So during discharging, what will be the VC infinite? Is it safe to consider as 0? If our capacitor will discharge, it has a tendency to till reach 0. Okay, till
Yes,
the point capacitor will lose all of its charge across the resistor. So VC infinity is equal to 0. Yeah, Niranjan. So VC infinity is equal to 0. Now VC at 0 is equal to how much?
1/3, sir. V supply.
VC at T is equal to 0 here. 2/3, isn't it? It is starting from the 2/3. Starting falling from 2 by 3 of Vs.
Right, sir.
Right? Yeah. So VC at 0 is equal to 2 by 3 V supply. VC at infinite again 0. So it will again follow the condition of discharging transient. So it will be 0 2 by 3 V supply e raised to power minus T on by tau. Okay, equal to V supply. Okay, so we can cancel out V supply. Okay, so e raised to power minus T on by tau is equal to 3 by 2, isn't it? So 1.5. Okay. Now we can take log on both hand side. Okay. So 0 minus. So it will be plus. Okay. So ln into e raised to power minus T on by tau is equal to ln 1.5. So minus T on by tau is equal to ln 1.5. So, but why it is coming one? Okay. Here V supply by 3 was there, right?
सर इधर V supply by 3 होगा ना?
Exactly, Sangeeta. Yeah, I missed that thing. Thanks. So we can cancel out that as well, right? 3. So now 3 by 2, so 1 by 2. So again, it will follow the same. That's why, because in my back of mind, I was sure that ln 2 will come. So ln 1 by 2 here, and minus ln 2. Okay, so minus ln 2. So T on is equal to tau into ln 2. And what is the value of tau here? During charging, what is the value of tau? Sorry, during discharging of
2.5.
capacity. Yeah,
2.5
2.5 kilo. Excellent, Niranjan. So 2.5 kilo into ln 2. Yeah, and it is 2. I'm going to say. So this is the expression of the on time, and we can calculate here itself. So 2.5 into C. So C also we forgot. So C is 0.25 into 10 to the power minus 3. Okay. So if we calculate, this will cancel out. So 2.5 into 1 by 4, 1.25. 2.5 divided by 4 into ln 2. 2.5 divided by 4 into ln 2. So 0.433. 0.433. So T on is higher. When discharging, it is discharging faster, isn't it? It is discharging faster. T on, do not get confused. T on means charging. T on is when our output is high. So discharging time of capacitor is equal to 0.433 seconds. And charging time of capacitor is equal to 0.77, 77 something, right? 779. So as we said that during discharging, there is only one resistor, so it will discharge faster because time constant will be smaller. And during during charging, it has two capacitor. Its current has to flow through the two capacitors, so its charging time will be slower. So in that fashion, we are able to calculate discharging time of capacitor as well as charging time of capacitor. So is there any doubt in this or till this point? Okay,
No, sir.
so we came a long way from the circuit operation till waveforms, and finally we are able to calculate on as well as off time. So now let us see what are the problem statements. So yeah, so high time of Vout, which means high time of Vout means discharging of capacitor, which is nothing but 0.4. How much we calculated? 0.433 seconds. So we are able to solve fourth and fifth part. I don't know why it is working slow today, my screen. Just so these two very important things we have calculated. So if we know off and on time, can we calculate frequency of output voltage? Please let me know what is the value of output voltage frequency.
Yes sir.
Yeah, so it will be
दोनों को ऐड करके बाई कर देंगे, मतलब 1/j
yeah,
कर देंगे
exactly
दोनों को ऐड
1 by T on plus 1 by T off 1 by 433. Excellent, Niranjan. So this one will be the frequency of. Okay, so 1 by 4.44. Oh, sorry, no, not in this place. Point 433.779. So 0.82. Mm, 0.824 hertz. It's coming out like that, but that frequency is so slow, isn't it? So anyway, if that is the answer, okay, so maybe data might be in that fashion, but that is the answer of this. So as it is mentioned by NS also, so 0.824 hertz. So that will be the frequency of output, which is quite slow, isn't it? So we are done with 4, 5, 6. Okay, now 1, 2, 3. Peak to peak value of VC. What will be the peak to peak value of VC? 3 volt. Yeah, so peak to peak will vary from VCC by or V supply by 3 to 2 V supply by 3. So V supply is 9. So the variation is 3 volt. Any doubt? Anybody have this doubt? Any doubt in this part? Niranjan has, Nenes has answered 3 volt. I hope Niranjan, you might be also able to get 3 volt, isn't it? Sangeeta?
ये सर बी सप्लाई
सर ये
से बी
रिपीट
सप्लाई बाय 3 सर्वाई करेंगे.
Yeah, Niranjan, you are saying something?
ये फर्स्ट वाला सर थोड़ा सा नहीं समझ में हमको.
Acha, peak to peak value we see. Okay, so you see the waveform here. So see, this is the peak to peak value, right? So 2 by 3 we supply, and here this we supply by 3. So this much is only peak to peak, isn't it? So it is charging till 2 by 3 of we supply, discharging till 1/3 of we supply. So the difference is the peak to peak.
Right sir. Okay, thank you sir.
Right? Yeah. It's good to clear out all the confusion. Whether it is very small doubt, please do not hesitate to ask. As Niranjan had done. Thanks a lot, Niranjan. So
Thank you sir.
yeah. So first part is also done. Okay. Now when VC is rising, what is the nature of output voltage? So output is high or low when VC is rising. I'm not going to go to waveform or
No.
circuit. Low, exactly. Yeah. Any doubt here?
No sir.
Okay, cool. When VC is falling, means when VC is discharging,
High.
the nature of output is high.
High.
Okay, so see, the understanding the concept is very important, then you are able to solve all the part. Anything is asked based on that, right? Anything based on SLR also. So we are done with this IC 555 timer. Any final doubt regarding this concept? Any silly, any trivial thing? We can clear it out right now.
I think no, sir.
Sorry, I was disconnected because my Wi-Fi got disconnected. Just a second. Am I audible now?
Yes, sir.
Okay. Okay. I think my screen. Okay. Yes. Okay, so I hope everybody got this point. I was asking whether there is any final doubt. My screen is still not shared. Sure. Yeah, so any final question before winding up the session, related to IC 555 timer or, oscillator circuit with a Smith trigger? So basically all these circuits are used for, generate certain kind of frequency with, certain kind of signal. Because in all the electrical circuits particularly, we see certain types of input we are feeding, certain types of signals will be required. So from where you are going to generate such kind of signals. So these are how the circuits are connected so that you can, connect your circuit and you can produce your desirable amplitude with desirable waveform with desirable frequency. So that's the logic. Okay. And also, during the first part, we saw that a Smith trigger with integrator in cascade. So in that also, if you connect, further register in parallel with the, your integrator output will be tend to more sinusoidal, which might have been discussed during the lecture by the professor as well. So that was one point I wanted to mention. Just, if you want anything to get discussed, we can do, or any doubt, or we can wind up today's session. So सब बढ़िया, निरंजन, NS,
हाँ
संगीता,
बढ़िया है
ज्योति,
सर।
सब बढ़िया?
सर मैं
हाँ,
पूछ
बोल।
रहा था कि एग्जाम का पैटर्न सर मतलब ऑब्जेक्टिव टाइप का रहेगा या सब्जेक्टिव, मतलब
It will be subjective. It will be subject. Some objective question will be there, but it will be subjective. So it's better to, understand the concepts with circuit so that you can, execute your understanding there. So it will be subjective to answer your question. Okay.
Okay, thank you, sir.
Thank you.
Good night, sir.
Good night. Good night, Niranjan. Thank you everyone for joining. Bye. Thank you. Bye, NS. Thank you. Thank you, everyone.